In proposition 26, we're going to prove two more conditions under which triangles are equal, namely angle side angle and angle angle side. So this proposition will have two parts, first dealing with angle side angle and then angle angle side. So let's turn to the text. If two angles have the two angles equal to two angles respectively, and one side equal to one side, namely either the side adjoining the equal angles or that subtending one of the equal angles, they will also have the remaining sides equal to the remaining sides and the remaining angle to the remaining angle. Let's check out the setup. Let ABC and DEF be two triangles having the two angles ABC and BCA equal to the two angles DEF and EFD respectively. Let's draw all this out. So let's say this is our first triangle. That's going to be ABC. And also DEF. And we're also given that the two angles ABC and BCA are equal to two angles DEF and EFD. So ABC is going to be equal to DEF, and ACB or BCA is going to be equal to EFD, which is this one. And let them also have one side equal to one side. First, that adjoining the equal angles, namely BC to EF. So this is given, and we're going to show that it follows that the triangles are completely equal. First, we're going to prove that AD must be equal to DE. And he's going to prove this by showing the absurdity if they're not equal, or if AB is unequal to DE, one of them is greater, let AB be greater, and let BG be made equal to DE, and let GC be joined. So what's going on here? We're going to suppose that AB is the greater of the two. And if that's the case, by proposition 3, we can cut off from AB a portion equal to DE. So let's do that. We're going to call that point G. And we're going to say that this is equal to this. DE is going to be equal to GB, or BG as he says. And then we're going to let GC be joined. So we're going to join those two, G to C. Then he says, then since BG is equal to DE, that's this side to this side, and BC to EF, the two sides GB and BC are equal to the two sides DE and EF respectively, and the angle GBC, which is over here, is equal to the angle DEF. What follows from this? Notice we have these two triangles GBC and DEF, and they have side angle side, side angle side. They have that relationship, and therefore it follows from proposition 4 that these two triangles would be equal. Hence he says, therefore the base GC will be equal to the base DF. That's true. And the triangle GBC is equal to the triangle DEF. And the remaining angles will be equal to the remaining angles, namely those which the equal sides subtend, again by proposition 4. Therefore, the angle GCB, which is this one over here, GCB, we'll highlight that. Therefore, GCB is equal to the angle DFE. These two angles are equal. That's what follows from proposition 4. But, notice, but the angle DFE is by hypothesis equal to the angle BCA. Recall we had the equality between these two angles, the angle here at F, the angle here at C. But notice we're going to have a problem right here in this diagram. Notice that the angle GCB is a part of this larger angle ACB. Therefore, the angle BCG is equal to the angle BCA, the less to the greater, which is impossible. We've got this part being equal to the whole. and that's absurd. Therefore, AB is not unequal to DE. That's the supposition that generated this absurdity here, and is therefore equal to it. Hence, we can go back near the beginning of our argument, and this is what we've learned so far. We've learned that AB is equal to DE, because the negation leads to absurdity. And we have, but BC is also equal to EF. BC is equal to EF. That was part of the given. Therefore, the two sides AB and BC are equal to two sides DE and EF respectively, and the angle ABC is equal to angle DEF. Notice we have side angle side, side angle side, side angle side. Since we have side angle side in both, we can use proposition 4 to infer that the base AC is equal to the base DF, AC is equal to DF, and the remaining angle BAC is equal to the remaining angle EDF. Just another usage of proposition 4. Therefore, given angle, side angle, that relationship between two triangles, we may infer that the other side over here, those are equal. These angles are equal, and that these sides are also equal. That is to say, the complete equality of the two triangles. That takes care of the first part of the proposition concerning angle, side, angle. And now we move on to angle, angle, side. So many of the givens will be the same. ABC is going to be given to be equal to DEF, and ACB will be given to be equal to DFE. But instead of these two sides being given to us to be equal, he says, again, let sides subtending equal angles be equal as AB to DE. So now we're going to suppose that these two are equal, as we have angle, angle, side instead of angle, side, angle. I say again that the remaining sides will be equal to the remaining sides, namely AC to DF and BC to EF, and further, the remaining angle BAC to EDF. And how are we going to demonstrate this? We're going to investigate whether the side BC is equal to EF. And similar to the first part of this proposition, we're going to suppose that they are unequal and show that that leads to absurdity. For if BC is unequal to EF, one of them is greater. So let BC be greater if possible, and let BH be made equal to EF, let AH be joined. So once again, we're going to suppose that BC is the greater of the two. And if it is, then we can cut off a part of it equal to EF by proposition 3. So we're going to do so. Let's call this point H, as he does. So that BH is equal to EF. And he says let AH be joined. We'll do that. Next he says, then since BH is equal to EF and AB to DE, the two sides AB and BH are equal to the two sides DE and EF respectively, and they contain equal angles. That is to say, they both contain this. So notice again, we have side angle side, side angle side, in the two triangles ABH and DEF. Therefore, those two triangles are equal. And he's going to make a bunch of inferences from this. Therefore, the base AH is equal to the base DF. And the triangle ABH is equal to the triangle DEF. And the remaining angles will be equal to the remaining angles, namely those which the equal sides subtend. Another usage of proposition 4, side angle side. Now the key inference, therefore the angle BHA, that's this angle right here, BHA, is equal to the angle EFD. EFD is this one over here. This angle and this angle are therefore the same by proposition 4. But notice, we're going to have a problem over here. But the angle EFD is equal to the angle BCA. Therefore, in the triangle AHC, I'll highlight that triangle. Triangle AHC. This one over here. The exterior angle BHA is equal to the interior and opposite angle BCA. So notice that this exterior angle over here, that's an exterior angle of this triangle, that's now equal to one of the interior and opposite angles. But recall, we proved that that's impossible in proposition 16. This exterior angle is greater than both of these opposite and interior angles. Hence, we have an absurd situation here in this diagram. Therefore, the supposition that generated this absurdity, namely BC being unequal to EF, is going to be false. Hence, he says, therefore, BC is not unequal to EF and is therefore equal to it. Here's what we've learned from that little argument. We've learned that BC is equal to EF. But AB is also equal to DE. AB is equal to DE. Therefore, the two sides AB and BC are equal to the two sides DE and EF respectively, and they contain equal angles, namely this angle here at B, this angle here at E. Notice we have side, angle, side, once again, and we're going to, of course, use proposition 4 again. Therefore, the base AC is equal to the base DF. These two are equal. The triangle ABC is equal to the triangle DEF, and the remaining angle BAC, which is over here, BAC, is equal to the remaining angle EDF by proposition 4. And that wraps up this entire proposition. So we've seen that we now have angle, side, angle, and angle, angle, side in our arsenal to make inferences about triangles.